All right. Well, happy Monday, everybody. It's week 6, and it's November. Tomorrow is election day. I think early voting is going on, so you can vote today. You can vote tomorrow. Tomorrow's the last day you can vote, so cast your ballot if you can vote. And yeah, we'll see. We'll see how the results come out. But anyway, I want to keep talking. We didn't cover everything in the Matplotlib. Matplotlib. I don't know how to pronounce this, but we didn't cover everything here. Again, this is kind of the tools that we have for visualizing our data. It pairs very well with Pandas, which is kind of the primary tool that we have for working with data frames. And so I want to finish this notebook, and then I'll introduce Seaborn as well. And so, yeah, this week we'll kind of just spend on the topic of, I don't know, exploratory data analysis, which is going to be important for doing stuff. So anyway, I'm going to start off here. I'm going to load up our packages, Matplotlib, NumPy, Pandas, and then let me jump down to, we talked about some of the different things you can make. All right, and so here we want to just print stuff directly from a data frame. And I think I did some of these examples, but okay, I got to make the time series, and then we'll make data frames based on that. And I think we did some of these things, cumulative sum. So when you print, if you call the data frame, so I can just do data frame.plot, and it'll create plots based on that. Okay. You can, if you have just a simple series, you can also create bar plots. You can just do data frame dot, the series, or just data frame, whatever you have, your series dot plot, kind equals bar, and you'll get a bar plot. And this one has positive and negative values. So we have things that go above and below. And again, here are just here's kind of like a two-way table. So if you have a two-way table, here I have two categorical variables. Across one way I have arbitrary states, and across the other I have these arbitrary sectors of the economy. And again, just random numbers here. Don't draw any meaning from it. But if you have a two-way table, you can create side-by-side bar plots. Okay, so you can create bar plots with the bars side by side, and this one I've got the industry sectors in across the x-axis, and the colors of the states in different colors here. But you can transpose. You can move. This one just shows moving the legend to outside the box. Okay, so here you add this line that says plt.legend, and then you put in this thing, bbox to anchor. Okay, bounding box gets anchored over here, upper left, or something like that. Okay. Here I transposed the data frame. So when I transpose the data frame, the states are along the x-axis, and the different sectors are the different colors. Okay, so these are both side-by-side bar plots showing kind of the same thing, but we're just changing whether the colors represent the sectors or if the colors represent the states. All right, and here I've moved the bounding box to this location over here. Okay, so these are just some of the arguments there. You can have a side-by-side bar plot. You can also stack them. Okay, and so here again, you take the data frame. You can put either one axis of the data frame along the x-axis, and the other axis will be basically the different columns will be the different colors. Okay, or you can transpose it, and then the columns go along the x-axis, and then the different rows become different colors. So these are probably some of the more common ways to display data from a two-way table, where you either have side-by-side bar plots or stacked bar plots. Okay, and so and these are just created directly from the data frame. Okay, you just title the data frame df data frame name dot plot dot bar or something like that. Okay, and there's a lot of these things you can always look up in. So you'll just say like pandas data frame plot. Okay, and lots of resources out there. ChatGPT is a pretty good resource for answering questions about pandas and data frames and things like that. But then my recommendation is always to use, always turn to the official documentation first. So here we got pandas.dataframe.plot. And so here you get a listing of some of the different kinds that you can do. Okay? And so on and so forth. Okay, let me do another example. So here I'm going to load data from the Titanic data set. Okay, so the Titanic data set it's kind of a well-known data set, and it's got information about passengers aboard the the Titanic cruise liner that sank. I don't know. They made a movie, several movies really, but anyway, we have information about whether that passenger survived or died during the disaster. We have information about the age of that passenger, information about the sex of the passenger, whether the passenger was in first class or second class or third class, and other information about their ticket fare and stuff. So apparently, you could ride for $7.25, or you could pay 10 times as much, $71, and that will get you in first class versus third class. Okay. Okay, and so for some of these summary values, okay, you can take a column like survived, and you can call .value counts, and this will just tell you how many of each value do we see. So we can see how many zeros and how many ones do we have. So we have 549 zeros, 342 ones. So we can create a series out of this. And if you have a series, you can also create a plot directly from this. And so notice the way I do this is I just chain methods using the dot. Okay? So my data frame is Titanic. And so I said Titanic.survived. That will select just the survived column. Titanic.survived.valueCounts will create this series. And then I do Titanic survived valueCounts.plot, and it's going to create a plot based on that. Okay? So it's just kind of like when you chain a bunch of nouns together to create, or a bunch of words together to kind of create like this complicated meaning, right? So I'm trying to think of I don't know, like sometimes we just chain words, right? Like I don't know, engine block cleaner or something, right? So it'll be like the block that, your engine block is a thing, and then you can have a cleaner for that, okay? And then, I don't know, the engine block cleaner sticker tag, it'll be the sticker tag that you apply to that thing. And you just kind of chain words together, and it add stuff. And that's basically what we're doing. We're just taking the Titanic data frame, we're selecting a column, dot survived, creating a series, dot value counts, and then we're creating a plot, dot plot, okay? And this is what we get. All right, some of the different columns, we have different different values here, okay? And survived, as it is here, we have zeros and ones, okay? And it interprets survived as an integer, okay? Because it's a 0 and 1, which makes sense. Those look like integers to us. But when we see the data frame, we know that survived 0 is actually the category they died, and survived 1 is the category that they lived. So here, I'm going to just change it from Titanic.survived, and I'm going to just do, I'm going to replace Titanic.survived with Titanic.survived, and then I'm going to use this function or method as type category. And that's going to basically take our integer thing and turn it into a categorical variable. And so my survived data started off as integers, and now when I ask for the data type, we're going to get category here, right? And then I'm going to take that column, Titanic survived, we're going to take the categorical features, okay, and we're going to just rename them from 0 to died and 1 to survived. So I'm providing a little dictionary with kind of a key here of how it should go. So Titanic.survived does that. And then, so now I can still do the same thing. I can do Titanic.survived.value counts. Okay, and so now I get the same information, but now it says died and survived. And then I can just do a dot plot as well. Let me see. Okay, so here, dot plot is not going to be I have to do kind equals bar. Okay, and so now we'll get labels. Rather than 0 and 1, we get the labels died and survived, which is always going to be more helpful, okay? Always more helpful to an outside observer. Okay, we can create a two-way table. There is a function in Pandas called crosstab, and you give it two basically categorical variables here, okay? I got Titanic.sex, Titanic.survived, and it will create a two-way table, and it will tell you, for those that died, this is how many females and males there were. Those that survived, this is how many females and males there were, okay? Or women and men, these were the sexes of the passengers here. Okay, so here's crosstab. This is a two-way table. And again, I'm just method chaining, okay? So I'm going to just take this two-way table, make a bar plot out of it, and make it stacked. And we can do that, okay? And so this is what we see. So we can see a greater proportion of women survived and a greater proportion of men died in the Titanic there, okay? If I got rid of stacked, here this would be kind of a side-by-side thing. So we'll have that, okay? We can make I'm going to make another variable. We're going to just call isChild. And I'm going to just do, arbitrarily, I'm going to just say under 8. Under 8 years old, we'll say is a child. I mean, we could have picked something else. And here I'm going to do a crosstab here versus, for isChild, true or false, okay? And then did they survive or die? Oh, I'm sorry. You can also do normalize, okay? Normalize equals 0. We'll take these from counts and turn them into proportions, okay? So this will do basically row Normalize equals 0 will normalize across the rows. Normalize 1 will normalize across the columns, okay? So the axis of normalization is what the 0 or the 1 means, okay? So here, 0 is for the rows, and so basically the row total will add up to 1 when you normalize them. So here we got 533 and 308 corresponds to 63% and 36%. 16 and 34 corresponds to 32 and 68%. And so from this, I can create a bar plot, okay? And because it's been normalized, they're both going to have the same height of 1. And so we could see for as far as children go, okay, for is child true, this ends up being, great, more children survived, at least under age 8. Under age 8, closer to 68% survived, whereas if you're over age 8, only 36% survived. Here, I'm going to create a group by, okay, and we're going to take these variables. We're going to group by sex, child, and survived yes or no, okay? And then we're going to count how many passengers. We're going to basically do a count of each. Okay. So I did a group by, and then we're going to count. And so now I have a series, but I've got a multi-index. The multi-index has 3 levels to it. Okay. We have sex, okay, for women and men. We have sex for children and non-children. I guess people over age 8 still, that still feels really young, okay? People under age 8, and then whether they survived or died. Okay. And so with a multi-index, you can unstack them. And if you unstack them, now I'm going to get a column for died, and I'm going to get a column for survived. So here, I can create a stacked bar plot, okay? And, it's a little, it might be tough to read, okay? But it says sex, comma, is child. So these are adult women, and these are, children, girls, right? So female is child false, okay? Female is child true. So not very many children, not very many girls aboard, but this is what we have. Okay, male, adult, false, a lot died. Okay, male, true. So these would be, I guess, boys, young boys, and there weren't very many on the boat to begin with, but you see the difference, the different proportions there, right? And so I don't know. Was this a thing in the movie? There's kind of this idea of like women and children first as far as like getting on the lifeboats and stuff. And so this is a little bit of illustrating a little bit of some of those results there. Okay. Okay, so as far as unstacking, so here we unstacked and we did died, survived there. Here we can unstack and then we can sum, okay? And so this is the thing here. So we unstacked, survived and died, and then this is just, I think, how many people we have. So survived and died just gets combined here, okay? So we had a total of 290 adult women and 24 girl children, okay? And 551 adult men and 26, children, boys, okay? And we can take that, I'm gonna call these row totals, and so using these row totals, I'm going to do a division so we can get proportions here, okay? So basically, it's like I wanted to do normalize here, but it's a little bit tough to do that, okay? So, but now now I get normalized values here. Okay, so I wanted to kind of just add them across, and then I wanted to divide by how many. So 75 divided by 290 and 6 divided by 24. So this gives us our proportions. Okay, so that each row adds up to 100%, and now I can create a stacked bar chart. Okay, so this everything adds up to 100% now. Okay, so basically we see this. It's because it's hard to tell the proportions when you're dealing with the counts only. So here, this will turn everything into proportions. Okay, and we can see as far as adult women and girl children, the proportion that survived is similar. Okay, but as far as adult men and boy children, the proportion that survived is greatly different. So anyway, these are just some of the different things that can be done as far as you manipulate your data in pandas, okay, using some of the different tools you have, like creating row values, row counts, calculating proportions and such, right? And so these are different ways you can do it. And then once you have that, you can visualize it just by calling plot on that resulting object. Okay, let me, oh, that's the wrong, sorry. I wanted to give you your view quiz. Oops, okay, something is stuck. Okay, we can also generate some random values, and so this is going to simulate rolling some dice here. Let's see. So here I've got, I'm going to create a data frame. I'm going to just do some random integers from 1 through 7, and then. So this will be basically like one dice roll, and then I'm going to create a column called 2, and I'm going to take the random values from the first column, df1, and then I'm going to also just add another random dice roll. Okay? So the first dice roll could be anywhere from 1 through 6, okay? And then when I add a second dice roll, those, that's like throwing 2 dice, and you can get any value from 2 through 12. What's going on over here? I didn't publish the quiz? All right. It says published. Let's see. Week 6.
I think the module might not be.
Oh, the module itself is not published? Oh, yeah. That'll do it. Okay. And I'm still trying to get logged in over here. I'm having Wi-Fi issues here. Okay, so anyway, uniform distribution there. When you have 2 dice rolls, when you combine 2 uniform distributions, the sum of 2 uniform distributions forms a triangular distribution. And that's what we see here, right? There's basically one way to get a sum of 2, 2 ways to get a sum of 3, 3 ways to get a sum of 4, 4 ways to get a sum of 5, 5 ways to get a sum of 6, 6 ways to get a sum of 7, 5 ways to get a 8, not 4 ways for a 9, 3 ways for a 10, 2 ways for 11, 1 way for a 12. And so we get this triangular distribution. And, it generalizes to when you have a continuous distribution too. Continuous uniform distribution also creates a triangle when you add 2 of them together. Okay, let me see if I can pull this up again. All right. Letter D is your first view quiz answer. D as in dog. D as in dog is your first view quiz answer. Okay. Here I'm going to say, all right, what happens when you take 3 dice rolls, 4 dice rolls, 5 dice rolls, and we're just going to keep adding them. Okay, so what happens if you add a uniform, another dice roll to 2 through 12? Then your sum can be anywhere from 3 to 18. 4, then your sum can be anywhere from 4 to 24. Okay, but it gets increasingly difficult. Like if you roll 4 dice, what's the probability that you get a sum of 4? You have to get 1s on all 4 dice, which is pretty tough, okay? That's 1 in 6 to the 4th power. So I don't know what that is. 36 times 6 is 216 times 6 is 1,296, 1296. So 1 in 1,300 to get a sum of 4 and 1 in 1,300 to get a sum of 24. But anyway, you can still create a histogram and you can create a plot of this. And so, you start off uniform, then you get a triangle, then you get something. And as you keep adding these uniform things, the distribution starts to look more and more normal. At some point, eventually, the sum of uniform distributions does reach the normal distribution. You get something that looks like this. All right. And so anyway, this is just a quick little thing. And then, you could change the... Here I said alpha equals 0.5. You could change the stuff. I don't know, edge color. Is that, I forget. I don't know if that's, okay, so that's hard to, that's kind of hard on the eyes. But anyway, you have that. Okay, so that's, that wraps up that notebook. All right, and then so I'll start this one on Seaborn, and I probably won't finish today, and we'll continue on Wednesday, and then this week I want to kind of just do like a full, just an example of exploratory data analysis or something. Okay, so Seaborn is a visualization tool designed for exploratory data analysis. Okay, so as far as stuff that you do in data science and data analysis and things like that, a lot of times your initial phase is exploration, right? You get this new data set and you just kind of want to explore it and look for things without necessarily searching for, you don't want to just throw it into some machine learning algorithm and say, hey, give me some results here. So the exploration is, a lot of times is, all right, what if I split the data into these groups? Okay, will I find differences between this group and this group? So that's kind of a lot of the exploration, right? If I separate my data based on gender, and we look at what proportion voted this way and what proportion voted that way, okay, are we going to see a difference? If I split the data set on, college education, those who have college education, those who don't, those who have, right, how do these different groups, vote or respond to questions or things like that? And there's kind of a lot of things. And the more you kind of split things, or you might find, okay, overall, this is the trend we see, but then if you focus in on, I don't know, this particular section or this segment, right? If you look at this particular location or state, things don't quite follow the rest of the trend. And these kinds of things are interesting, right? So you can say like, overall, blah, 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 this group voted this way, in large numbers, but people in this particular state didn't follow that trend, and there might be some kind of interesting factor, right? Some kind of economic factor going on in that location that could kind of explain some of these differences, right? I'm just making up some silly example here. Well, maybe silly is not the right word, but just these are the kinds of things that you want to do in exploratory data analysis. You just kind of try splitting your data in different ways. And a lot of times, how do you know if there's a difference? Well, again, you can kind of create these two-way tables and do proportions and stuff. Sometimes you just want to create some quick visualizations and see if you can pick up and notice different trends and patterns. And so Seaborn is a package, and it's built on top of Matplotlib, okay? So Matplotlib provides all of these kind of plotting functions, and Seaborn is kind of a collection of, I don't know, like templates, quick little templates that you can kind of throw in your data in, and they're all designed so you can kind of get a quick read, visual exploration as you're exploring your data here. Okay, you might have to do pip install Seaborn. Okay, so if you try to run this thing and you get an error, you got to open up your terminal, pip install Seaborn. Okay, restart your kernel in VS Code, and then it should work. Okay, so let's go ahead and take a look at this. And let's try this. Okay, so we're gonna do import matplotlib, import numpy, import pandas, import Seaborn, and then the convention is Seaborn as SNS. Seaborn is SNS. Okay. Okay, so Seaborn is for visual exploration. You can use Seaborn occasionally to say fit a model, okay, but it's not designed for statistical analysis, right? So in R, I don't know, do you guys take 101A yet? Maybe, not yet. Are you scheduled to take that? Yes, okay, so you're gonna do like regression, you'll do like classical things, you'll create linear models. Have you guys used LM in R? Yes, okay, all right. So in R you use LM, you get your slope, you get your intercept, you get your coefficients, all of these different things, and you can create plots and whatnot. Seaborn, you can also fit a linear model, but you will not get your coefficients, you will not get R-squared values, you will not get a lot of these things that we would consider necessary as part of a formal linear regression analysis, okay? Because Seaborn is not designed for statistical analysis in mind. It's designed for exploratory data analysis. So when you say fit a linear regression, it's just going to say, all right, here's kind of the line. If I wanted to draw a line, this is the line I would draw. And it's not meant for you to do like residual analysis or do those kinds of things. So it's purely the philosophy of Seaborn is for visual exploration, not for statistical analysis. Okay, I'm going to load a data set. This is the Palmer Penguins data set. Are you familiar? Have you heard of this data set? The Palmer Penguins data set? Basically, I guess penguin researchers, they went down to some islands in Antarctica because that's where the penguins live. And they went to Torgerson Island and Biscoe Island and Dream Island. And there's different species of penguins. We have the Adelie penguins. I think let's look at pictures of penguins. Okay. So we're going to look up the Adelie penguin. How do you pronounce this? Adelie? Okay, the Adelie penguin? I don't know. Oh, I was not expecting that. I thought it was going to give me a pronunciation of this. Okay. All right, well, this is what they look like. The Adelie penguin. Okay, and then there is the chinstrap penguin. And they have this little, we don't have a little sound button. Okay, this is what we have here. Oh, look at that. Okay, chinstrap, and then I think we have the Gentoo penguin. They're so cute. Okay. Adelie. Okay. That's the only one that has noise, huh? All right. I gave to you already. I already donated. Please remember this. Hide appeals for a week. Okay, anyway. So anyway, this is our penguins. Look at these guys. Okay. All right, and we're gonna we're going to do some data analysis on these things. And so we have different islands. They measured the bill length and the bill depth and the flipper length and how heavy the penguin is and the sex of the penguin. I think the original research was curious if male and female penguins of the species had what they call sexual dimorphism. Basically, like, male lions and female lions, like the males get these big manes, and you have these characteristics that allow you to distinguish between members of the different sexes in the species. And so they were just wondering if there's a difference in these things. But also in our data set, we can just say we can easily pick out differences between some of the different penguin species. Okay, so with Seaborn, kind of your basic tool is drawing a kind of like a histogram, okay? But we call distribution plot. This is going to be a plot so we can explore the distribution. Our argument is data comes from this data frame, and then the variable we want to look at is flipper length in millimeters, and we'll just create this plot. And you can see, so we create the plot using SNS, but then we call plt.show. So because SNS is built on top of Matplotlib. So when you call snet.dispplot, distribution plot, it creates a plot in Matplotlib, and then we call plt.show, which is basically our matplotlib.pyplot. Okay, and so this is what it looks like. So basically, we just get a histogram. Okay, and we see, oh yeah, it's bimodal. Okay, bimodal histogram. Now you can change some of these things. You can do bin. You can change the number of bins. You can also add what's called a rug plot. Okay, a rug plot it's really hard to see, but you get, and it's a little bit more useful in a continuous distribution than a discrete one. But you get little tick marks at each of the different values that you see. Okay. Instead of specifying how many bins you want, rather than saying bins 20, you can do bin width. And so here, bin width of 2, and basically each of these bars represents 2 flipper lengths. Okay. You can also specify cut points for each of your bins. So you could say, I want to cut them at 170, 175, so on and so forth. And you can do that. And so here, my last cut point was at 200. So basically, I'm just artificially truncating my data at 200 here. And that's why this distribution plot looks so different from everything else. Okay. So these are all basically just variants of making a histogram. And you might wonder, why would we want to do this? Well, we have a few other options. You can also add a kernel density estimate, which is often a handy little feature. A kernel density estimate is kind of the idea of, please draw a smoothed out line that fits the histogram. Okay, so I don't want to get into the computation or the math behind drawing it, the smoothed out line. But basically we're asking, hey, can you draw a smoothed out line for this thing? And you can do this. And this is, a little, like if you wanted to do this manually yourself in Matplotlib, it's possible, but it's annoying to do. Okay, and Seaborn makes it easy. You just say, hey, distribution plot KDE equals true. It's going to add the kernel density estimate. Okay. You can also change the kind equal to KDE, and then you just get the kernel density estimate only. Okay. Then you don't get the histogram. You get just the smoothed out line. And then another thing you can do is the empirical CDF. What is the empirical CDF? This is a cumulative distribution plot. Okay, CDF. The CDF is your cumulative distribution function, which will range from 0 to 1. And so basically at 170, flipper length 170, we have no, what proportion of penguins have a flipper length less than 170? 0. Here, let me hide this one. No, wait. Okay. I want to hide my... Okay, there we go. Just having trouble clicking here. Okay, so none of my penguins have a height, flipper length below 170. And then we could say, okay, what about at 190? Okay, at 190, around 20%, if you counted all of the penguins, around 20% of the penguins have flipper lengths below 190. And then, and then eventually when you get to 230, 100% of the penguins have flipper lengths below 230, okay? If you have something bimodal, what that corresponds to is you have two regions that have steep vertical increases. A steep vertical increase corresponds to a peak here, okay? So we have a steep vertical increase around here and another steep vertical increase around, I don't know, 215, around 190, 195. Yeah, 190, steep vertical increase, another steep vertical increase around 215, okay? And then when you have an area of flat regions in your empirical CDF, that corresponds to basically areas where there's few observations, okay? Few observations. So, what proportion of penguins have a flipper length over 200? 0.6. What proportion of penguins have a flipper length over 205? Just a couple more, 0.61. What proportion of penguins have a flipper length over 209? Not very many more, like 0.62, because there's very few observations in that range, okay? But then when I say, hey, what proportion of penguins have a flipper length below 209? It's like 62, but then what proportion of penguins have a flipper length under 212? There's a big jump there because that corresponds to kind of a spike in the histogram there, okay? So this is the empirical CDF, and it's always going to go from 0 to 1. And again, steep vertical increase means lots of penguins in this region. Flattish regions means not very many, okay? So your typical UCDF looks like this, and that corresponds to like a normal thing, right? So flat-ish regions correspond here. Steep increases is where there's a peak here, okay? So that's if you want to just look at one variable at a time. Very useful thing, important thing to do. Sometimes you want to look at two variables at a time, all right? And so if you wanted to look at two numeric variables, is there a relationship to flipper length and bill length, okay? So your traditional thing, so again, we got two numerical flipper length and bill length. Two numeric variables, okay? Your traditional plot you would make would be like a scatter plot, and we can do .dist plot here, and when you do this, you will get basically a heat map, okay? A heat map. And this will say, hey, this is where you have a lot of observations, okay? A lot of observations with lots of penguins around, I don't know, 190 and a bill length of 36, okay? A lot of observations here. We have no penguins where the bill length is 35 and a flipper length is 220, okay? We have one penguin, I don't know, with a short flipper but long bill, but not a whole lot. Not a whole lot where you have flippers of 190 but bills of 55, okay? Or 0, pretty much right there. That's the default. You can say, hey, I want a kernel density estimate, okay? Kernel density estimate, you're going to get this basically a contour map, okay? Contour map. I don't know, are you guys used to reading contour maps where you have, so this would indicate when you see the lines close together, that means steep like hill, okay? And you have kind of this large open, like when the lines are spaced out, it's kind of like flat, gradual changes in elevation here. All right, you can do things like add a rug plot. You'll get rug plots along the axes. And then hue equals species. Watch what happens when I do hue equals species. That's going to color these things. We're going to separate based on our species of penguins. Adelie, what were the other ones? Gentoo chinstrap, okay? And so we see, now we get KDEs for the Adelie, and then Gentoo, and then so we say, oh, you know what, this, we can see like this, the structure I'm seeing here is a mixture of 3 distinct populations, okay? We have the Adelie penguins look like this, and the Gentoo penguins look like this, and the chinstrap penguins look like this, okay? And so the Gentoo penguins, whatever, they have longer flippers, okay? Longer flippers, longer bills, okay? Adelie and chinstrap, their flipper lengths are kind of similar, but the chinstrap penguins have longer bills. So, I don't know, let's look at this. Here's the Adelie, similar flipper length, shorter thing, and I guess, yeah, I don't know. I can't tell. But I guess if you get a ruler, measure their... What did they do? They capture these guys and then go... I wonder. Okay. All right. So, you can do that. If you don't... if you just do one variable, okay? One variable, you see, oh, okay, yeah, we got these 3 different groups here. Okay. And this, again, this explains... So flipper length, remember, we didn't separate it out by color, but we saw this bimodal business here, okay? And this kind of reveals, when you separate it out by color, what's going on, right? We say, oh, okay, we've got these 3 different species. And 2 of them kind of overlap, so that's why we're getting one thing. Then, all right. So... the bimodal here, the KDE. You can also take this. This is our distribution plot. Instead of drawing a KDE thing, you can also, when you have you can call multiple equals stack. And basically, it's the same, these same heights, but then we broke them out, okay? We said, all right, this is many chinstrap, this many Adelie, and so on and so forth. And it colors them out. It's a little hard to read sometimes because it's, green, orange, and blue, and so they're stacked on top of each other. That's what we have there. Okay, a joint plot. Joint plot will give you the scatter plot. Okay, this is the scatter plot. And then you get the distribution. So this thing right here, this is just this and this are exactly the same, okay? This histogram and this histogram are exactly the same. This one's it's just a little bit squished, right? And then you get the underlying dots, and you can see, okay, oh yeah, these underlying dots for bill length and flipper length correspond exactly back to this heat map that I made, right? So here's the heat map, and basically the heat map is kind of like a 2-dimensional histogram of this, where if you drew a grid here and you counted how many dots are inside each box, and then you colored, like if you have one dot in the box, it gets a light blue, and if you got a bunch of dots in the box, you get a dark blue. That's basically what this heat map corresponds to. And we get the exact same thing here, okay? And then what I can do is I could take this exact same thing, and then I can just do hue equals species. All right, and then we get our colors. Okay, the blue and the orange and the green. We get the distribution plots. Again, this KDE thing looks just like this thing, but just shaded in. Collapse these. So I want to, all right, so we have this. And then you can also see The scatter plot corresponds very closely to the kernel density estimate plot here. Okay, so the blue, orange, and green correspond to here as well. So that's what you have, and then if you wanted to, you can also, instead of the dot plot, you can just have this. So different options as far as exploring these. Oh, okay, I have run out of time. How many answers did I give you? Just one? Okay, I will give you, your second one answer is the letter A. A as in apple. I'm going to stop the recording.